All right, so let me give you the menu briefly of what you're going to hear indeed. You're going to hear 4 talks the next 2 hours. I'm going to start talking about where is prior information encoded in the brain. Then it's going to be followed by Hannah, who will answer the question, how can a group of this size possibly work together? And then Stefano Fusi will talk about who else is using this data. Stefano is not part of the collaboration, but he'll show you how you can leverage it to answer other questions. And we'll finish with Anne, who will address the question, how can we be sure our approach of pooling data will work? So let me just indeed briefly remind you what the International Brain Laboratory is about. It's a consortium of about 21 labs, I believe. Half of them experimentalists, half of them theoreticians who decided to join forces to collect the first brain-wide activity map in animals performing a perceptual decision-making task. Now, the slides here highlights the PIs, but I think it will come to no surprise to all of you that those are not the guys who did the work. The people who did the work is this incredibly talented team of postdocs, students, staff who worked tirelessly over the last 6-7 years to collect this unique data set. So just briefly, IBL was created indeed with a few core principles in mind. The first one was indeed large-scale neuroscience. So large-scale data set, brain-wide, but also that requires a large-scale collaborations because none of the lab could possibly collect this data set at the time at this scale. Second big principle was reproducibility, and Anne will come back to this issue in her talk. Third one is everything was done in the spirit of open science, data sharing. Our data set was actually released pretty much the day we were done curating the data. It's freely available already, and it was way before we had even a chance to analyze it. And finally, we strongly believe that all of this had to be done through collaboration of experimentalists and theorists, because we believe it is, of course, the future of neuroscience. But here at the SCGB, I think I'm preaching the choir. OK, so the task is a task in which the animal is in front of a screen. There's a stimulus, a grading that appears on the right side or the left side of the screen. The animal has a little wheel here that controls the horizontal position of the stimulus. And the task is to bring the stimulus in the center, in which case the animal gets a reward. Otherwise, it gets a timeout. We control the difficulty of the trials by varying from trial to trial the contrast of the stimulus from 100% to 0%. And then we also control, and that's going to be what this talk is about, the prior probability that the stimulus appears on the right or on the left side of the screen. You can see here the evolution of the probability for the right side that evolves across trials and across blocks in a typical session from 0.8 to 0.2. And importantly, the duration of those blocks comes from a truncated exponential distribution, so they're extremely hard to predict when they're going to switch, and the switches themselves are unqueued. So the only way the animals can figure out that there's a prior in there is by monitoring the past sequence of trials, right? And that's, of course, critical information for the animal, particularly at low contrast. In fact, at 0 contrast, it's the only way the animals can perform above chance. That's by monitoring this prior information. OK, so while the animals is performing this task, we're recording with inserting 1 to 2 probes. We did so in 139 animals, 459 sessions. We collected 600,000 neurons, non-QC neurons. From that, we extracted 75,000 neurons, and those are the ones that you're going to hear about, where we're applying very stringent quality control criteria on them. They come from 242 regions, and when you add up the volume of those regions, you get about 95% of the brain volume, hence the name brain-wide map. And I'm sorry the video is stopped. Let me see if I can. OK, and when you look at this, you see something quite remarkable. Look at this massive increase in activity in the brain as the stimulus goes on and the animal starts responding, right? Totally contrary to what you heard from Carlos. Beautiful input modulated activity in the brain. Well, there's a bit of a trick here. We removed all the ongoing activity. We removed the baseline activity. If you retain the baseline activity, then you get the most boring video you're going to see at this conference. You can look at it, there's nothing to see. If you squint, there's a little bit blip of activity. So that's the 1.5% of activity that Carlos was talking about. It's meaningful. It drives the behavior. But it is definitely in this ocean of spontaneous activity. All right, so the first problem we had with IBL dataset is how do you show the data? We have data from the entire brain. So we decided to adopt the Swenson map, which is a 2D projection of the mouse brain, where you get to see the entire brain at once. Now, of course, I'm not going to take you through all the different areas. All you need to know for this talk is that this is the hippocampus here, cortex is on top here, frontal area here, the back, occipital cortex, visual cortex is here, basal ganglia underneath, thalamus, hypothalamus, midbrain, hindbrain, medulla, and cerebellum. All right, that's all you need to know. So indeed, we have this huge data set. It's available here. You don't have to write down the links. You can go on the International Brain Lab website, and you'll find all the information. In the first paper that's coming out soon, we're describing this data set, its properties in particular. We're looking into the neural representations of all the behaviorally relevant variables for this task: visual stimulus, choice, feedback, wheel speed. And I'm not going to do justice to this data set. There's tons of different analysis and way of looking at it, because today I would like to focus on another behaviorally relevant variables, which is prior information. Where is it in the mouse brain? So now, why are we interested in this? Well, one of the influential theories of brain function posits that animals behave like Bayesian observer. And what it means is that when they want to extract some some information about a variable of interest, S, in this case, it will be the side of the stimulus, right and left, based on some sensory evidence, here an image, and some prior knowledge, then the Bayesian observer tries to compute the posterior distribution over the side, right and left, given the image, which it gets through Bayes' rule by multiplying two terms, the likelihood function and the prior. Okay, so obviously, understanding where the prior is represented in the brain is a key step toward understanding how this is implemented in neural circuits. Now, we're not the first one to ask this question. There are quite a few theories. And on the two extremes, if you look at the literature, you'll see that there's one scheme that's, I would call the late inference schemes, that hypothesize that what sensory areas do is to compute likelihood function, which are integrated with a prior late in the process in higher order areas, leading to the posterior, which is then used to guide behavior. If that's the way the brain is organized, when you decode the prior in the brain, what you expect is to find it just in those higher order areas, frontal area, secondary motor cortex, orbital frontal cortex, places like this. On the other extreme, the brain might be a gigantic Bayesian network. So a Bayesian network is a network of variables that are connected to one another in which you can do inference in any direction you like. It's much more powerful, so let me give you an example. Say you want to know what syllable a speaker just uttered, based on sound and visual lip movement. If you have a Bayesian network like this, given the sound and the lip movement, you can recover the posterior distribution over syllables. But you can do more than that. If I only give you the sound, you can predict the syllables, and from that, you can get a probability distributions over possible visual movement that the speaker produced. And you can go in the other direction. Given just the image, you can get the syllable and then predict what the sound should have been like. So much more powerful, a bit tricky to actually fine-tune, because you can easily get confirmation biases in such architectures. So if that's how the brain's organized, and I inject a prior somewhere in that network, what's going to happen is that it's going to update all the other nodes, and it's going to effectively percolate through the system. And so when you decode the prior, what you expect to see is the prior appearing all over the brain, right? So you might think, great, there are lots of papers that are talking about this. They're listed under here. And do they have the answer? So here's the problem that we encounter when you start doing it, is that when you read those papers, you quickly realize that they don't always use the same species. They don't always use the same task. Even when they use the same species and the same tasks, they often manage not to train the animals in the same way, which lead to different results. And they often record in 2 to 3 areas. So how do you integrate all this data together? And this is where our approach can help, right? We have one species, one task, one training protocol, 242 areas. So we can look at the whole brain at once. OK, so before I show you the results of the decoding, I need to convince you that the animals are using the prior. Those are the psychometric curve of all of our animal average and condition on right blocked and left block. And you can see that zero contrast, the animals are performing above chance. They're not at 0.5 because they are indeed tracking this prior, right? Good, so now we can decode the block prior, the true block prior over there. Well, bad idea. Remember, the animals cannot know where the true block prior is. They have to infer it from the past sequence of trials. So instead, we're going to decode what we call the Bayes optimal prior, which is the best estimate of the prior you can get given the sequence of trials, right? And which we get by inverting the generative model of the task. So this is the kind of plot that we get when we do this. The light blue line here is basically the Bayes optimal prior for this particular session. We do it for all the sessions, and that's what we're going to be decoding, this light blue line. And we're going to do that at a very specific time. This is the typical sequence of trial, a sequence of events that you see in a given trial. Okay? And we're going to decode between trials, when there's nothing on the screen and the animals are sitting there and instructed not to move. So this is the 88% of activity that Carlos was talking about yesterday. What is it representing? And obviously, one of the things it does is that it represents whatever expectation you have about what's about to happen in the world. Okay, after a lot of work, 2 or 3 years of work, as a matter of fact, this is the map we finally obtained. In blue are the areas where we can decode the prior significantly, and they represent about 30% of all the regions. Critically, we find regions at every level of brain processing. So we find them in the late areas, orbitofrontal cortex, cingulate cortex, but also in very early sensory areas, primary visual cortex, LGN, all the way down to the thalamus, and then in the sensory motor areas, stegonomotor cortex, caudate putamen, intermediate layers of supracolliculus, and then a slew of other motor areas, but that was expected. Okay, so you might be convinced at this point, that's it. We have answered our questions, but the reality is there's lots of controls you want to do. There's lots of confounding factor in this experiment. I'm not going to list all the controls we have in the paper. I just want to cite like 3 of the most important ones, in my opinion. First one is we check that the prior decoding cannot be explained away by body postures and eye position, right? So maybe the animals are sitting in a weird way that's correlated with the prior, but that doesn't explain our data. Second, we find correlation between decoded prior and behavior. So if we decode that the prior is currently 0.7 to the right from the neural activity, the animals are actually performing at 0.7 to the right on zero contrast trials. Third one, we found that this encoding of the prior persists throughout the trial. So I just showed you the intertrial intervals, but we see it when the stimulus is also on the screen. Okay, so looks like we may have answered the question that we asked at the beginning. Our data are quite consistent indeed with this Bayesian network idea of brain circuits. So that answers my first question. Now I want to turn to the second one, which is, what is the subjective prior used by the mice? Because I played a bit of a trick on you. I told you the animals are using a prior, and then we decoded the prior, but I didn't show you that the animals are using the Bayes optimal prior. So are they? For that, we turned to Bayesian model comparison, and we tried a lot of different models for this. I'm not going to show you all of them, only 3 of them here, and we tried to figure out which one best account for our data. And to our surprise, it wasn't the Bayes optimal model. It was one that we call the action kernel model. Okay, what is this? Well, this is a model in which the animal update their belief about right and left according to their own action, right? So if they go right, they increase the probability, the prior probability that the stimulus will be right on the next trial. Excellent idea if they were correct. Totally idiotic if they were incorrect, right? You're updating in the wrong directions. But that's what we see. So in fact, we're not the first one to see this. Ilana Witten, who is part of the collaboration, was the one to tell us, hey, guys, did you check this? Because we've seen this in our animal. So 7 labs have reported that this seems to be a strategy adopted by rodents in this kind of tasks. All right, so some of you might be thinking at this point, well, that's not a strategy. That's dumb. That's just a repetition bias. What those animals are doing is they went right, and they do it again next trial. But they're a little smarter than that, okay? We computed how many trials in the past they're looking at to compute this prior. And we found that they use an exponential kernel with a time constant of about 5.5 trials. So it's not just repeating the last trial, it's looking at what happened in the last 5 to 8 trials. Now, what's really interesting is if you ask yourself, which value of this kernel, or this exponential kernel, maximizes reward rate, it's exactly 5.5. So the animals may not be using the best model, but at least they're tuning it right so that they get as much reward as possible. Okay, so I want to end with one last control, one that's partially inspired by something that I think Meredith over there mentioned yesterday, that you really don't want to just rely on Bayesian model comparison and just behavioral data. And the reason that there's a real risk that if you do this, you're going to reach the wrong conclusion and end up with a paper in Nature Human Behavior, as you did yesterday. OK, so what we did here is we're going to take advantage of this asymmetry between the behavior of the action kernel model after correct and incorrect trials. After a correct trial, the action kernel model updates the prior in the right direction. So performance on zero contrast trial should be high. After an incorrect trial, you update it in the wrong direction, so your performance should drop. Okay? And that's what we find when we simulate the action kernel model. We check that you don't get that with the other model, in particular the Bayes optimal model that doesn't have the asymmetry and does the right thing and update everything in the right direction. You don't see a difference here. Okay, all of that are just simulated agents. Now, in the behavior of the animals, we see the same asymmetry. That's why, in fact, the action kernel model wins the Bayesian model comparison. The question now is what's happening in the brain of the animal, the neural prior. So what we did there is we decoded the neural prior from the data, and then we played the task. We actually tried to guess on zero contrast trial ourselves, is the stimulus going to be on the right or on the left, and we looked at our performance. And when we do this, we get that gap, all right? Confirming that what's in the brain of the animal seems to be really dependent on the few actions of the animals, right? Confirming the action kernel model. It seems to be in the brain. OK, to conclude, we have finally completed the first brain-wet activity map that we know of, particularly in decision making. Again, it's available here. It's an incredibly rich data set. If you're working on decision making, you should really check it out as kind of a way to confirm whatever hypothesis you're looking for in your own data. And you're going to hear that from an example of that from Stefano Fusi. And then we use this to try to answer these long-standing questions about the kind of inference strategy we find in the brain. Our decoding the prior suggests that the brain is indeed a big Bayesian network. And finally, we found that animals seems to be using their past action to update their prior belief about the state of the world. So thank you very much for your attention. I'll be happy to take some questions.
Hey, Alex. Very cool. You're referring to the prior here, right? And in this context, the prior is a prior about a lot of different things. It's a prior about where the stimulus is going to appear on the screen. It's a prior about which action is more likely to generate a reward, and various things in between. If you were to try to decouple those, do you think that all priors would be everywhere, like Todi? Or would they be, like, would the prior about the stimulus be just in the sensory areas, the prior about which action is likely to get a reward just be in the action areas?
OK, prior on action or bias on action, for instance, like a tendency to go more right on the so we checked for that. On this one, at least, we looked for that, because we haven't looked at all possible interpretation. But this one is an important one. So one possibility that the animals just, given their prior belief, they're going to tend to go right no matter what. And that would trigger in the psychometric curve a horizontal shift of the psychometric curve, whereas a prior about the stimulus would shift the psychometric curve horizontally. And on that we checked, and it seems to be mostly a sensory prior.
I guess I meant something slightly different. The prior about the likelihood of reward given a particular action. So it's a prior about the stimulus response or the action value contingency rather than the stimulus contingency.
Yeah, that we haven't checked and we haven't distinguished. I would like we should talk offline about how you would do that. My experience is they all often boils down to the same thing, so they're hard to distinguish, right?
Thanks. I was wondering if you've looked at all at the distribution of the prior as a function of the block when the block switch happened, and whether or not that changes how widely you see it distributed or not. Or whether or not it might indicate there are some special hubs that compute this early on.
Yeah, we would love to do this and to figure out where is it computed and address that, but so far everything we've tried has failed. We haven't found a clever way of doing this. It's also updated very quickly. So after a block switch, the animal recovers the prior with a time constant of 5 trials. So it's actually very consistent and it's very fast. So this is what you don't have much data to look at, basically.
Hi, Alex. It was very interesting to see this representation of the priors in many different functionally distinct areas. The question is, given feedback between those areas, is it possible that that is masking some sort of feed-forward processing that you might be able to see if you compared the latencies of the representations in these different areas? Do you see anything like that?
So it's related a little bit to the previous question. It's very difficult to look at the timing of the prior update because we don't know when the animal is going to do this, right? Especially given that it seems to be related to actions. And when do they die after the action? We can't really time that. At least we haven't found. Maybe Carlos will be clever enough to figure out how a way to time it exactly. So we don't really have the answer to that. We haven't been able to look into this.
So it's very interesting. It's very reminiscent, when people play the Wisconsin car test to check for perseverance. That's one of the diagnoses for schizophrenia, that you persevere because you update the prior based on the action that you just take. You stay with the action, regardless of whether it was successful or not. And I was wondering whether this type of analysis, what wouldn't have neural data, but just looking at the behavioral data, would it be consistent with the kind of model you propose?
So yeah, we haven't looked into this, but like, for instance, Sophie Deneve had some beautiful paper on this because to you, I don't think I need to tell you that loops in Bayesian network is a nightmare, right? You start having confirmation biases. And Sophie Deneve has been arguing that depending on how the system is tuned, you get depression or you get schizophrenia, right? So yeah, she has a paper on that. That's super interesting. And it'd be interesting to see whether we see this kind of problems, for instance, in a rodent model of schizophrenia. But of course, we haven't done that.
Thank you.
Hi, Alex. This is maybe a follow-up on Manish's question, because I think the experiment has kind of been done by actually a member of the IBL. It was Tom Mercich-Vogel. So if I remember correctly, he has a task.
Who Mercich-Vogel on this?
Yeah, not on this task, but where the animal uses the same behavior to report detection of a change in the temporal frequency of a drifting visual gradient. And what they do in the task is that within trials, they dynamically vary the prior, because if the change is going to happen early in a trial, the change is drawn from a distribution that's shifted in one direction, and if it's going to come late in the trial, it's shifted in the other direction. And in terms of the neural results, if I remember correctly, they find something qualitatively different, more consistent with your first hypothesis, which is that the influence of the prior shows up only in late, like secondary motor cortex striatum, not in sensory areas. So I wonder if you know about that work and sort of how you think it relates to these results.
So I can't comment on this work specifically, so I don't. But one thing I know is that indeed, I think the conclusions will depend on exactly the detail of the task and what it is that the animal is confronted with. So I don't want to say this will what you're going to find in all experiments that manipulates the prior. But the fact that we find it in this particular task suggests that it is definitely diffusing. Right. So that would be the main message.
So I'm not sure if this can be alive again, but just saying the progress of the chair to ask. Get my own mic, I can wave it at you. The slide that I expected you to show at the end was a slide that showed what the spatial distribution of the areas were that represented the ACT kernel. Because what you showed us is where the Bayes optimal prior was represented. But I wanted to know whether those same areas represented the ACT kernel signal and equally well, and whether there was a more specific set of areas that represented that.
Tough questions, because despite the fact we have enormous amount of data, when you divide by 242 regions, we don't have that many neurons per region, especially in some of the regions. So this region by region analysis is tough to do, but we did something that this is Charles Finling, the guy who did all this work, came up with a very clever control. I don't know if I can explain it quickly, but basically he looked at the fluctuation in the neural activity in the brain, and he asked whether those fluctuations are consistent with a kernel of 5 trials. It's something where he doesn't even decode the prior. He's just asking, is the dynamic the same as the prior? And that actually we find a strong correlation for that. But we did it on a kind of brain-wide level. Like area by area, I don't think we have enough data. And what's really nice is that if you use the stimulus kernel, which is the one where you update according to the stimulus, you don't get that correlation.